Okay. So I uploaded the term project. The term project is about a dam failure. It was a real project, real failure in Mississippi, and this is how it looks like. You know, there was embankment, and it was working like a reservoir, so just trying to hold the water. It's a small dam, and if you look at the problem there, in this area, you can see the sand seam. You know, so the dam has some kind of sand seam. So basically, because of the sand seam, what's going to happen? Any idea? If you have a sand seam within the dam,
That's the lower formation. Sand seam, right?
Sand seam.
yeah, sand seam.
Yeah. That would work like a pipe.
Good. Yeah, that will work like a pipe. Means there will be a high possibility of piping, right? And seepage loss. So basically, for this one, there was like it was the issue with the site investigation or poor quality construction, you know, and it failed. So you need to consider a few things. So some of the things are true and some of the things I made it up. Just to make it a project. So I give you the dimension. The dimension is pretty close. You know, I didn't make it up, but the soil properties I give you here is a fabricated soil property. It's not the actual soil properties, but I give you like some of the data so you can run them. That's why I try to give you some close numbers. So the first thing is you need to do all the hand calculations here. You know, these are the hand calculations. So 1, 2, 3 are the hand calculation that you need to do the seepage analysis for the embankment and the foundation soil and come with the calculations. You know, but I try to upload some of the things. So usually that was part of the project 1. But in the project 1, I also wanted to do like some kind of hand calculation for the repair design. I feel like it's not a good idea within this time frame, so I took it out. I just want you to do the hand calculation up to the failure, you know. And once you do the hand calculations up to the failure, then you have to run the same analysis in the slide, which we're gonna cover like next week, you know. So and then we can work on like, so basically we're gonna cover it next week. So you need to run another set of analysis of the same thing and trying to find out like what is the seepage, you know, and do the comparison between your hand calculation and the seepage analysis using the slide. So once you do that, then you need to do a repair analysis, you know. So the repair analysis, someone give you a cross section looks like this. You need to validate it, come with your own judgment. If you feel this is good, you keep it. If you feel this is not good, you come with your own solution. But this part is not hand calculation. This part is you just need to create your own profile. And this part you have to run and do the actual design, but using the software. And so you have to do like all sort of the slippage analysis, stability analysis, and you have to get all the cases, you know, for the seepage, for the stability. You have to look at like the changes in the water, different things, and based on that, you will come up with your solutions or your design, or you just support this design. I don't know what is that. I really don't know. You know, when I saw your result, I will know what is that, because I haven't done analysis on this. I just made the project. And but this project will give you a flavor of the real project, because this is very close to the real project, you know. And you have to present your results. You have to present you have to prepare a report. So I have a limit of 10 pages, but you can add additional results in the appendix. But in terms of your write-up and your justification, you know, has to be within that 10 page, like the right part. But the figures and all other sort of things like hand calculations, you need to add it in the appendix, you know. So that's the project. You have 45 days or so to do the whole thing. So it's gonna be due on 24th, right? So our final week is when? 27th to 1st, or the 4th to 8th?
8th December, 8th and 9th December.
What is the
7, 6 and 7. Number 6.
November?
Yeah, 6.
Is,
7.
is the midterm?
The final.
The final is December.
December.
December 6th.
Yeah.
December 6th is the final?
Yes.
Yes. Okay, so November, when is the fall break? Okay, 21 to 26. So class resumes on 28 to December 2nd, right?
Mhm.
28 to December 2nd is the final examination for graduating students. None of them is graduating here, right? Okay, so that's our final week. That's our dead week, right? So that's from the, so you'll get one more week. So it will be due on Wednesday. Our class is Tuesday, right? So you'll get till Tuesday, the following Tuesday. So I'll take it. Can I take the date? Okay, so this is not in term. Project. Okay, so I need to edit the term project. Will be due on okay, so it will be due on class resumes on 26th, right? So it will be due on 28th. Because the week of 20th, this is closed. That's for Thanksgiving. So after Thanksgiving, that is 28th. is your project view. Okay, so I'm changing it to 28, and I'm gonna make it 28 to look at. I don't need to give you an extension. That's it will be available till the deadline. You can submit early, but
It's a group project, right?
yeah, it's a group project. We did that in the same group. Okay. So how many groups we have? Seems that the project is short. Because the work is divided in 3%, right? It's not a lot of work. Okay, but I will ask tough questions. So because it's a town project and it's a group project, so there is a possibility that someone take the heavy load, the heavy lifting of everything, and others they don't do anything. So my question, the way I'll ask you the question is, if you're presenting one part, you need to answer question from other part. You know, basically, I'll ask the question in terms of the concepts. You know, if you can explain it without doing anything, you're good to go. But if you cannot explain it without doing it, it's basically it's very tough. If you're not doing it, but trying to explain it, then you will not be convincing. You know, so even if you're not doing it, you have to understand the whole thing. Okay, so that's due on October 28th. So when you guys are leaving?
8, 9,
29. So 28 is fine.
Yeah. We finish everything for proposal. There is a proposal. 27.
To proposal is 27. Okay, so you have, you know, your timeline. You know, so it's 20. You know it from today. So if you start working on it on 27th and try to submit it on 28th, then you'll be in trouble. But if you start working on it now, then it's much easier, right?
We need to do the numerical analysis like this or
No,
You know, in slide.
like
In slide. So I'll cover the slide next week. So I'll cover the slide next week or the following week. So by end of next week, okay, so today's what? Today's October 17, right? By October 31st, you will learn everything that is needed to do this project. Okay? The rest of it is your work, you know, but based on my work, it's like I'll try to cover most of the things in stability by today, and then I'll go for the like my lecture and everything will be done by November 7th. I really have nothing to discuss there, you know, because I'll go over 2 lectures, 24th and 31st. One is on the slippage, the other one is the slope stability, and then I'll go over the details of the slope stability. So by 31st is done. 7th is my review class. 14th is like I can go over any discussions if you want me to discuss, you know. And then the following week is, so our lecture and everything will be done by then, you know. I may cover something like maybe I can cover some other topics to discuss on 4 or on 40 class, you know.
we need to submit the term paper.
Yes, you also need to submit a term paper. Okay. So the term paper, for the term paper, I can allow you more time. I have no problem with it. So for the term paper, the deadline is maybe the 5th, because I need to check when the grade is due. So the grade is due on on 12th. Okay. So if the grade is due on 12th, so I may allow till the 8th of December. But remember, you have the final, right?
Final will be April.
The final, yeah, final will be taken. Yes. But final will be, even the final will be take home. The final,
Will be similar to earlier one. The timeline will be similar to earlier one.
the timeline will be similar to the earlier one. So yes, the take home, and in the take home exam, you also have the model. You know, so since it's going to be take home, I will allow 24 hours in this exam, in the final. So in that timeline, you need to run both of the things, like you need to have the some of the problems, and then you also have to do like some analysis. You know? Okay, so I wanted to be clear on this. So you have enough time to get prepared, you know. So I suggest you start working on it as you can, you know. So the part A, you're ready to go, you know. If you start it early, you finish early, you know. And now in terms of the term paper topic. So for the term paper topic, you had a presentation on the homework one, right? You all have to present on the failures, right? And each of you presented a different topic.
Yeah.
Different time.
Different time. Write a term paper on that failure type.
Period time.
On that failure type.
Same day.
Yeah, it's on the failed time, the causes of the failure, case studies, targeting the one you present. You know, you need to cite at least 5. Paper, presentation, report, whatever, at least 5. I'm not assigning anything because each of your topic is different, but it's not a group submission, it's an individual submission.
So we have to submit term paper on the failure of that time.
Or similar. Or similar. If you don't find enough literature on that time, then similar failure on other times. Failure type. I'm targeting the failure type. So let's say if you presented Titonem, right? So if you're presenting Titonem failed because of what? Piping failure, right? So you can also go back and find out the tons of papers in terms of the piping failure. All you have to do, I think, you either go to the ATSO website or USSD website and you'll find tons of the materials on this. You know, those are there. There are many case studies. All you have to do, you review it, you talk about it. Now you have much better understanding. When you started to take this class, you have a limited understanding, right? You're just trying to present what you have seen, but I really want you to present it in terms of your language, your understanding, you know. So what you have seen, and based on that, what is your feelings about it in terms of the video? And then you also need to recommend few things like what went wrong, what are the things they could have done right, and what is the lesson learned out of it. You know?
So that will be a term paper.
That would be a term paper, 10-page paper.
we are writing on the piping failure or written on that return dam for piping failure.
It can be both. It's up to you. It's up to you. You can write on the Titan dam failure, but even if you're talking about the Titan dam failure has many literature, so you should be able to find out like at least 5 papers. So you can just talk about, you can just write a paper on the Titan dam failure. You know, so that's on the Titan dam, but there are some other dam failures.
Also, Oroville dam failure.
You have even more. You have even more because I think you also find the NSF report on this. You know. What else dam we had?
Louisiana,
Oh.
Hurricane Catherine.
You'll find hundreds of documents on that, not one. Do you know what is the output of that failure?
Code have been changed. People are thinking about changing all the building codes.
Okay, so what change has been made?
You can see period analysis, considering a newer kind of frequency period or return period during design.
What is that?
Maybe, for example, if it is 100 years, now they are thinking about considering 500 years.
Thinking about or the change has been made?
Change has already been made.
So is there any update on the design code?
Both can be in the.
The
Because
design code has been updated based on that paper. Now you have to consider the 500 years return period. Do you think the 500 years return period is enough?
more than enough.
More than enough?
It's good for Netherlands.
Good for Netherlands. How about Mississippi? Mississippi is not Netherlands.
Mississippi is not too low from the sea level, like Netherlands.
But
But there is a weather climate change,
okay, so what
the
happens?
pattern of rainfall.
Has
Pattern
changed.
of rainfall is
changed.
changing.
Okay, so if the pattern of rainfall is changing, then what is gonna happen?
Huge amount of rainfall within a very short time. This kind of situation may arise.
Huge type of rainfall within a short period of time. So the reservoir capacity might not be enough, right? So if the reservoir capacity is not being enough, then what might happen?
It cannot sustain the extra load, extra hydrostatic load imposed by the discharge of river.
Okay, so let me ask you a question. So whenever you have the extra rainfall, will it care if you consider 500 years or 1,000 years in your design?
So we have to include the climatic variations, like the duration of the heavy rainfall, and also the scenarios are changing, like before it was heavy rainfall for a shorter period of time, but now it's been, the time span has been changing, like in Libya, that we saw that heavy rainfall was for like 1 or 2 days, that was supposed to be like 3 hours or 4 hours max. That kind of impact need to be addressed in the.
Yeah, did it happen to anywhere in the world? The same condition? Not only in Libya?
In, I guess, there was heavy rainfall there was flood, right?
There, yes.
There was flooding there.
So, and anywhere? Usually this type of condition never happens in New York, right? It may happen in Seattle, but not in New York, you know? And
Also in Bangladesh, it happened in Dhaka. There was so much rainfall that the water.
there are a lot of showers.
There is some Libya.
Okay, Libya, Dhaka, and
And,
For heavy
and
rainfall.
India, like,
But
you know, There was like
Himachal Pradesh.
Himachal, yeah, yeah.
Jalpaiguri.
It's Jalpaiguri, we had.
They had a similar condition.
Yeah.
And then, how about Pakistan?
Afghanistan, Afghanistan is the upgrade.
Last year,
Last year there was a flood in Pakistan.
there was a severe flood in Pakistan, right?
Yes.
It made the major destruction in Pakistan. It never happened in Netherlands. And everyone is following the code made by Netherlands.
Usually in Netherlands, all the coastal dikes are made for 500 meters, 500 years, it can be done, 600 years.
Netherlands doesn't have the hurricane. Right? So you have to make your own code. Tough problems. Isn't it? Okay. So in this case, what is the biggest challenge in civil engineering infrastructure?
You need to sustain the load.
Making it climate adaptive.
How we are going to make it back? Okay, so if you want to make it climate adaptive, it's a very good question. But what is the major challenge to be climate adaptive?
The structure, depth and whatever we are thinking, that's not adequate,
How?
because we don't know what is coming.
Uncertain.
Uncertainty.
Very good. You don't know what is coming. That is the biggest challenge. If you know what is coming, and if you can predict it, what is coming, then give like designing a structure is not difficult. It's beginning. You know, if you have the right expertise and if you find the right people, you can build anything. Who has the right experience and right knowledge about the infrastructure system. But the problem is the load you're considering for the design is not valid. The loading conditions, you know. Now, if your loading condition is not valid, the infrastructure is invalid. It doesn't do the purpose.
And most of the loading is like transient condition, right? It's not steady condition.
Yeah, it's a just happened. Like you take it, like you wake up in the morning, you see it's raining, and then it's raining and raining and raining. And not predicted the condition like that. So if that type of raining happens, there will be a definite failure in one type of infrastructure. Definite failure, no matter what. But it does.
Dams and rivers.
That comes later. The first thing, which is not being designed for, is
Stormwater drainage.
exactly the stormwater drainage. All the stormwater drainage, you cannot undo it. For the dam, you can. If needed, you can add a flat wall or you can elevate the height, right? But how are you going to update the stormwater drainage? How are you going to update it? Is there a way you can change the design or size of the stormwater drainage? No. So that's the biggest market for a civil engineer to work on.
Stormwater drainage.
No. What do you have in the stormwater drainage?
Water.
What is the infrastructure? Pipe.
Oh, concrete pipe.
So what topic to work on? If you want it to be leads, what topic you should work on?
Hydrology. Hydrologic modeling. Stormwater is all about.
In a design project, who makes the money? In a civil engineering project, who makes the money?
Contractors.
Okay, so
We need to start the business of pipe making.
exactly, if we start the business of the pipe making, because all the pipe become impact, right?
You have to go for the steel pipe in that case.
No, basically, the system, the way it's gonna work is you really cannot change it, you know? So what you have to do is you have the same piping system, right? It's kind of impossible to come up with a system where you really don't have the pipe. Now, do you know how the flood control is done in US?
What?
Flood control system in US is being conducted. How the flood control can be conducted. How the flooding works.
Discharge
You have a discharge,
out of
you have a
control.
loss of volume, right? If you cut off some volume, if you cut off some flow, your major problem is you have a peak flow condition for a long period of time, and you have a very high peak flow condition. So the best idea to do it is all you have to do is you just cut off the peak flow, right? So cut off some flow from the system. If you can create a distributed system where you create some storage, you know, if you can create the storage within the system, then your same pipe network is good to go. Right?
We have to just give the pipe system enough time to discharge those, like.
Yeah, it says like, and you just need to cut off the water from the system. And then it's like a peak and off peak hour, right? In electricity. So in the power business, you have the peak hours and the off peak hours. So if you can just do the right ratio between the peak and off peak hours, you are solving the problem, and you don't need tons of money to do that. So how you can do the ratio? The solution is there. Everyone knows the solution. All you need to do is you just need to build something, add something in the system to do that. So all you need is you need some piping, some pumping station, right? You need the detention pond, right? You need to add detention pond within the system, right? As long as you can add the detention pond and store the water whenever the peak flooding condition is coming in, you are solving the problem.
That is the problem.
What is the problem?
Because like cities in New York or like in Dhaka, there is not enough space for the detention pond. You need space, like it's a gravity flow. If we pump it to somewhere else, but we need the place.
We need this space. So why is this space? There is only one way you can get this space.
Going underground.
Ocean.
Up or down.
Up or down, yeah.
Either you go up or you go down. But you have to build a vertical structure, not a horizontal structure, right? And it's easier to build down, right? So that is creating market for whom? If you're doing the city, if you're doing all the down structure, underground structure.
So Tesla was a genius creating the boring company. We need to do some boring.
Absolutely. Why not? So another thing is the tunneling, you know. The tunneling will be one of the most important topics in next 20 years. Because all of they were tunnel pro. Right? In the dam, do you need a tunnel?
Yeah.
Where?
Underground.
Where? In the dam. Why do we need a tunnel? So let's say you have a dam, and the dam is like on the verge of a failure, like in Libya. They have overtopping, they don't have anything to do for the overtopping, right? Now you have tons of dams, many dams all over the world. How you can create a climate adaptive infrastructure system? You don't have enough money. If you go and ask them, okay, demolish the dam and build something, is it possible? No, right? So what you need to do?
You have to make an efficient discharging system.
Very good. You have to make efficient discharging system. So whenever you have like those type of condition, you just need to let the water go away. You let it flood because that creates less problem than the overtopping, which will do a devastating problem, right? But whenever we are talking about it, we are already accepting that we will allow the flooding.
Yeah, because all the dams have like emergency spillway. That the main idea of the emergency.
Yeah, the emergency spillway is designed for a condition that is not happening anymore.
We need to change.
And it's difficult to create an emergency spillway. So why do you create this spillway? How do you create this spillway?
There's the dam. Beside the dam.
If you don't have this space,
Creating a tunnel.
creating a tunnel. That's what I'm saying. That's why the tunneling and the underground infrastructure becomes very crucial.
The time has to be done earlier. Can we?
Everything has to be done earlier. That's why you need to do the once you have the water coming, all you have can do is scale.
So like, when we have already built the dam, can we do the?
Yes, you can. Why not? The dam is already there, but you need to add some spillway, 5 or 10 different spillways. You just add this spillway. So if you see, you cannot discharge the water. How the water will be discharged? Either the water go on the top, or the water will go underneath the dam. You need to let the water go away. That's your problem, right? So if you let the water go away from the dam or even in the levee system, you're solving the problem. Because you have to do it in a controlled way, not in an uncontrolled way. The water will pass through it anyway, right? So if you just let the water go away, you solve the problem. Most of the problem is being solved. If you just control the water, because all the problem is you have excessive water, right? Isn't it? Okay. There's a very good project. If I look at the project is very good. And I think it covers the whole course. So whatever we have learned throughout the course, one project covers everything. So please start working on it. Don't wait for the last. If you wait for the last minute, it will be only. Okay, so I want to discuss that with you then. I also wanted to go over the slope stability lectures, and I think I can finish it today. It's not too much. Okay, so my question is, why slope fail?
Why slope fails? Because of the loosening of shear strength.
Okay. What if you don't have a loosening of the shaft? Let's say you have a slope. And there is already a word is slope stability. Means there is a problem of instability, right? So there is always a component of instability integrated in the slope. Do you know what is that instability comes from?
The slanting nature of the slope.
Okay.
The slantedness of the surface.
But why it doesn't happen on the vertical wall? Like on the retaining wall? Isn't it they have the same problem? Like this. This is vertical, right? It's standing, no problem. It's standing. If I keep rotating it, after a point, it will fall down. So what is the instability here?
Angle of repose or something.
Angular because it comes up with it has the friction surface.
The uneven surface.
Who is gravity, right? So what is gravity is doing
Just creating movement.
on this one? Moment comes from a force.
Yes.
So first you need to identify the force.
Dividing the force in cos theta and sin.
Okay, it's dividing the force into cos theta and sin theta. So is the whenever the force is gravity is always working
Downward.
downward, right? Perpendicular to the plane. Not perpendicular to the plane. Is no matter what it says along the vertical direction. No matter what, right? So if it is working in the vertical direction. So let me ask a very bad question, really bad question. So let's say you are on the North Pole. Which direction gravity is pulling? You are standing on the North Pole.
Radially,
Radially, right?
radially.
So it's like North Pole is here. You are standing here. Gravity is pulling it down. How about you are standing on the South Pole? South Pole is like this. Is it? So if you are standing like this, but you are standing like this over there, right? But if you look at from outside, you are standing like this. If you go outside, like go to a space shuttle, try to take a photo. You are just upside down. But you are still there. So the gravity is pulling you down, pulling you toward the
Center of
Center.
center of that, right? Okay. So the gravity is always there. No matter what, we cannot take off the gravity, right? No matter what. So if we cannot take off the gravity, we cannot take off the component of the gravity or component of the gravity force. That's one. There is another way of explaining. So that's one part of it comes from the gravity. There is another component that comes from the solids.
So self-weight,
The self-weight of the soil also creates instability, right? It goes upward, but it can move toward both ways, right? So let's say we have this stove, it's like this, right? And this, it creates a condition where like it has some areas and the component of that area is always work downward, W. So that W will have like some components working the other way, right? So when the component is working this way, that kind of create instability, right? So it's try to push the moment. But if you look at that, if you look at that, this W cos theta or cos alpha is pulling along this line, right? If it is pulling along this line, why we have the slip side? Why don't the soil just move?
Because of the collision between them.
Why it creates a slip side? Because the way the load is working, just common sense. I'm asking the question based on the common sense. So if the force is working, that isn't it the soil just move?
No, there is a vertical loop. The both are moving and combining those two, it becomes like this.
movement,
Moment,
Like a resultant force.
what is the result?
If you have two directional force, it goes from here. So here it is sliding like this. And vertical.
Yeah, that's your resultant force is W. So from W you have the W cos. The resultant force is W, which is vertically downward. That's stable. That's the most stable load, right? That pulls you down. No problem with it. Unless you're not punching through the soil, right? Your gravity is pulling it down. The best possible failure is the punching, right? Punching failure is a shear. But you're not shearing through the soil. Any idea?
And some reaction is working towards the horizontal surface.
Because it's not only this problem, there are some other factors too. We are not looking at the problem with, uh, with the eagle's eye or bird's eye view, you know, we're just looking at a small piece of it. If the soil needs to move, if the soil needs to move, soil cannot move only on a single piece, you know. So let's say only this piece of the soil is trying to move. Can it move? It will move. Okay, so let's consider this soil will move. So let's say this piece of the soil is trying to move. Can it move?
Only this portion cannot.
Which portion can go? Have you scooped in an ice cream?
Yes.
You did? How you scoop it?
Like creating a car arc.
Okay, can you just take it from a small piece?
No,
Why?
stable. Stable.
It's stable, very good. Let's say this part of the soil, the head soil is trying to move. So we are trying to scoop it. We can take it out if we scoop it with a excavator, right? But if we don't have that, then how you can take it out? If you take it out, then you have to scoop it. And when you scoop it, you have the least resistance when you scoop it. You know? So every time that the curvature of that failure is going down, so your resistance is coming up. You know, whenever it's moving, your resistance is going down. You
Can
have
be explained using more circle, right?
how? How? More circle is very complex. More circle just distribute your principal stress. Two principal stress and how you distribute this principal stress into other ways. That is more circle important. Isn't it? You know, that's how why the more circle is being developed, right? Like you want to distribute between the principal stress and the Cartesians, right? So any other plane from the principal stress, you draw any plane and you wanted to calculate that, more circle is the graphical method to do it. Is that okay? So that's one way, right? So if this soil is trying to move, it will push it down. And whatever the soil at the bottom will try to give a passive rest, right? So what is the passive rest? I won't let you move. That is the passive rest coming from the soil. So if you wanted to push any barrier, what is your best way to push the barrier out?
Right.
Find out the least possible energy, right? You don't need to fight with everyone. You just find out the least resistance, right? So you will have a least resistance when you try to have something like that. That's one thing, you know. That's how you have most of the failure, which create a slip surface. So you just go away, you know. Your load has to be mobilized. So when the soil started moving, it tried to mobilize it in a pattern. So the easiest way to mobilize it is creating a slip surface. That's why you see the slip surface. You know, that's how you create the instability. There is another way of explaining this problem. So, yeah, I'm trying to explain it in a very unconventional way, not in a conventional way. You know, so you can just feel. Okay, so let's say we have the soil, and within the soil we have a solver. So this is our ground line, and we're just looking at the point P, right? So within the point P, if we have a distributed pressure, earth pressure, how the earth pressure will look like? How to calculate that earth pressure? What is the earth pressure, by the way?
Bosing's theory, practically,
What is earth pressure?
practically. Bosing is formula.
What is the Boston's formula? Boston's formula is a different thing. Boston's formula give you the stress increase. That's not for your earth pressure. You build a building, you put a stress on top of it, additional stress. How that additional stress will be distributed through the soil, that is being explained by the Boston theory, not the earth pressure. Earth pressure is like a gravity. Earth pressure comes from the gravity, right?
Potential difference.
No, weight of the soil, right? The weight of the soil. So at this point P, you have a height difference H, okay? So all the soil on top is putting the pressure on top at this point, right? So what is your pressure? Sigma P,
UGH.
gamma H. That's your sigma P. What is your sigma H?
Horizontal,
Sigma H.
lateral,
So this is your vertical pressure, right? Sigma P. And what is your sigma H?
Active or passive? Yes.
What is active and passive?
sigma V by sigma is equal to, there is a constant. That constant is called, can be K naught K.
Yeah, that's the biggest problem. The way you learn it. Because you learn it the other way. You learn it the back way. You should learn it in the front way. Because to explain the sigma H, you introduce a factor. You don't learn the factor to introduce the sigma V and sigma H. Because sigma V and sigma H is there, always there. You need to understand how to convert between the sigma V and sigma H. So if you want a conversion factor or a factor to convert from the sigma V to sigma H, then you need to introduce something, a coefficient or something, right? That's how the coefficient comes into the play. Not you explain the coefficient with sigma V and sigma H. Isn't it? Because the coefficient can be anything. Today we are learning there is a coefficient and we name it. 5 years down the line, you come up with a new coefficient, with a new theory to explain the coefficient. But you cannot change the sigma P and sigma H. Because the sigma P and sigma H is always there. Isn't it? Right? Coefficient may change. Coefficient, we don't know. What is that? What is that? If you follow someone's theory, it's okay. Right? And is that coefficient is right? That's the direct question. The answer is no. It's not right. Because it's under predict and over predict. My question is why that coefficient is not right.
Not the exact.
When that coefficient is being given. Did I give a presentation on this? So my question is when that coefficient is being given.
It's been developed when the soil is stable.
Okay, Coulomb's theory,
Coulomb theory, Rankine theory.
right? So when Coulomb developed that theory,
Many years ago,
what,
1800 something.
800, 1800 something, 200 years ago. So do you think 200 years ago, Coulomb was so smart to come up with everything he did, come up with a graphical method, because he don't even a computer. And that guy is so genius that whatever he came up with is accurate. I'm just asking you a simple question.
We're considering it accurate. We're considering it accurate.
We are considering it accurate, but is it really accurate?
Check.
Yeah, there are many papers on that, and that proves it's not right.
Really?
Yes, why not? Because it's underpredict and overpredict.
So whatever we learned is down.
No.
No, it's 70 to 80% accurate. It's accurate with a certain factor. There is an uncertainty in that accuracy.
Everything is uncertain, but the question is how much uncertain we are allowing it.
You know, so the question is how much you can allow. Anyway, that's a different question. The major question I'm trying to ask you is the sigma H and sigma B is not equal, right? But there is one cases where the sigma B and sigma H is equal.
Cannot condition. Cannot condition.
No? Not at all. No way.
Excavation.
No. Saturated condition. Okay. Why saturated condition? Not saturated condition, but close to the saturation. Is only valid where the sigma B equal to sigma H when you don't have a soil, but you have some other material. What is that?
Water.
Water, right? Pascal's law, and Pascal's law is valid. Do you know why Pascal's law is valid? No.
That's also very experimentally good.
How?
Characteristics of the water, it
Yes.
transfers the.
Compressibility.
Okay.
Water is incompressible.
And
Water is incompressible.
And it
okay, so I got it. But his factor is 1. His K0 factor is 1. And it's definitely experimentally proved, right? These equations, Coulomb's formula and all other formula are also experimentally proved. But those experiments are soil specific. Let's say you do it for a sand. Soil is very uncertain material, you know, because it's a natural material. You don't have, it has a significant variability, you know. Since it has significant variability, it creates so many problems, you know. So working with soil is good. It's challenging, true. Okay. But what Coulomb did is great at that time, you know. He was much ahead of the game at his timeline.
He also formulated the electrical formula.
Yes, and we are much behind in our time. Especially in civil engineering. Right? In civil engineering, we design everything based on static conditions, right? Or based on the empirical formula.
Or you don't know, we just have it.
Then, So whenever we are considering the empirical formula, nowadays, if you wanted to really predict how much load is coming, we can develop that, isn't it? But we can do a performance-based design even 30 years ago, if we wanted to, right? But we never do that. We try to follow the same formula, the same old school formula, right? But other industry are disruptive. If you look at that, if you look at the technological disruption in other industries, they are like a rocket, and civil engineers are like riding the bicycle.
Will it change? Will it change?
Yes, it will change and it will disrupt everything. Because that's how society works. It's a matter of time. But it will change. It will change. It has to change. Isn't it? It's a simple common sense. All I'm saying. Right? Because all other industries, if you look at the computer engineering, electrical engineering, even the cell phones, right? The amount of sensor you have in an iPhone is unbelievable, right? And how much you pay for it? Maximum $1,500, including everything, right? Like the highest trim, only $1,500. And you go and buy a civil engineering equipment with one sensor, with that you have in iPhone. How much you pay for it? $5,000 to $10,000. Think about it. Your iPhone has more capacity than an inclinometer. To buy inclinometer, you pay $10,000. To buy iPhone, you pay $1,500.
Because safety is associated with everything. Cost will be higher, obviously.
No,
It's all about accuracy.
no, it's not about accuracy. iPhone is they use Geo-DART.
I mean, the civil engineering equipments that we use, like exclusively that we use, like we said that inclinometer. So the data they provide,
Because no one challenge inclinometer yet. That's why inclinometer is still possible. The only reason inclinometer is still having the market, no one else challenged that market. It's not a technological problem, it's a business problem. So many things will change. Anyway, so let's go back. Let's try to see it like what we are discussing. So you have a sigma p and sigma h, right? The connecting factor between the sigma p and sigma h is known as a factor, just a factor. We call it earth pressure factor, right? It can be K. We name it as K. K can be in different conditions, different time. It can be K naught, Ka, Kb, Kp, active pressure, passive pressure, all these things. But let's say, whatever the weight is, there is some sigma v and some sigma h, right? So let's say on this point, this is my most interesting, most favorite discussion. So let's say on this point, what are the contribution from this side and this side for this point? We have some overburden, right? So whenever we are talking about the sigma v, all the load is coming from the top. But whenever we are talking about the sigma h, what is also happening?
also getting stress not.
So this weight we have has a contribution laterally, right? That is causing the sigma H, not this way, the top load. So let's say my phone is here, I'm pushing it. I have a less chance that it will try to bulge out, right? Isn't it? But whenever I have something, let's say you take a ball, you push the ball and you hold the side, you'll see that because of that ball, it will try to push like on the side, right? So you have a weight here, right? This weight has some contribution toward this point, right? No matter what, whatever the K or something, it has a contribution. Okay, good. Now, if I try to draw it again,
So that means loading on the right side
has some impact on this point, right?
will induce sigma H.
Yeah. The weight on this side. This weight is contributing to your sigma. How? You take a retaining wall. I put it like this. Right? It's stable. Now I'm trying to put some load, side load on this. At one point it will start tilting, right? So it's pushing it. So which means if I add some soil, it has some component toward the lateral direction, right? That lateral direction comes from the weight, whatever the weight I have, right? So if I build a wall here, the soil will try to push the wall, isn't it? So if the soil is trying to pushing the wall, means it has a component. The weight component is pushing it, right? So at this point, whatever the load I have is coming from this side and this side, isn't it? Okay, good. So let me try to draw it again. So this is my point. I consider that I have a load distribution. So my vertical load is higher, my horizontal load is lower, you know. So I have something like this. I have a load distribution. Here, if I try to draw, my vertical load is higher, horizontal load is lower, right? Now, if I try to draw it in a different way, yeah? If I try to draw it, this is my vertical load, whatever the upward and downward is equal, right? My horizontal load, upward and downward is equal. Sorry, left and right is equal. If I make it a slope here, what might happen?
Left it is not equal.
Left and right is not equal, right? Which one will be higher?
Left one. Left one.
Left one will be higher. Like this?
Yes.
Okay. How about this load right here? You have a vertical one, you have a horizontal one, the left one. Most likely the right one is also equal, right? How about here?
Left one is
Much better.
Right?
Higher.
So your left is always higher than the right as you go close to the slope.
Also the up one is
Is lower, so but up and down is balancing out, right? But your left and right is not balancing out. You get my point? So if your left is getting higher, as you go closer to the slope, there is imbalance. Right? Okay, if I go here at this point, a little bit far, now you have some overburden, both sides. So let's say you have the left one and you have the right one. So if you look at different points, which are the points? If I look at those points like this, you know, which are the points will have more impact and which are the points that less impact in terms of the sigma p and sigma h.
Electronics are more.
The left one, as we go on the left,
Stability
More and
increases.
more stable.
Stability increases.
stability increases. We go toward the right,
Stability
Becomes
decreases.
more unstable.
stability decreases, right? So, which side will fail?
Right side.
The right side, and how the failure will happen? This surface, right? Especially depends on the areas where
Resistance is low.
you always have it's an inner force. It also comes from your gravity because sigma h is a component of the gravity, right? Isn't it? But who will try to keep it in place? You have an imbalance between sigma p and sigma h, right? So if you have an imbalance of sigma h. So all is happening is you have a summation of sigma h, right? Which is not equal to 0. So which is greater than 0. So you for each point, right? Whichever point you need to look at, you'll see that your sigma h is greater than 0. Now where it will fail? Whoever is trying to hold it in place. So that's an imbalance in the force. And in the someone will try to keep it in place. Will try to keep it in place.
Sigma v.
No. In the soil. This is the internal force working within the soil, right? So who will try to keep it in place? The internal strength, the soil strength,
Yes.
the shear strength of the soil, right? Cohesion and friction. We'll try to keep it in place. You know, so there will be a band of the area where you may have the points, those are not adequate to keep the load in place because of that imbalance. Now my question is, we started this discussion with a discussion of instability. Where is that where the instability is? Within the soil body, right? Is there a way it will be changed? Can we change it? Can we build something that there will be no instability at all? No? Is there a way we can have a condition there will be no instability?
But the shear stress is equal or higher than the vertical horizontal stress.
But it's always built in, right? Your instability is always built in. You make a slope, you have a problem built in the slope.
There will be instability. If I make a slope, there will be instability always.
There will be instability, no matter what. It will fail or not depends on how much strength you have. You know? And more instability comes if you have like more inclined portion, you know?
The slope is higher.
the slope is high. You know, as the slope gets like close to particle, it will fail, right? Particle fail. And as you make it close to the horizontal direction, your imbalance is going away, right? As when you are horizontal structure, when you are horizontal, you have both of them, right? When you are vertical structure, what happens?
You have no sigma h.
You have sigma h, but you have no balance in sigma.
Balancing.
This will go away, right? So you always have the push. And in between, you have an imbalance. How much imbalance you have depend based on that, it will fail apart.
Based on the angle.
Yeah, based on the angle, like how much the slope is. You know, I just wanted to give you the feeling how the slope instability works. You know, so now are you getting the sense like how the instability is there? So anytime you see a slope, think about it. There is instability, right? And how the instability is working. If you are not getting the same, you cannot solve or you cannot design it in the right way. You know. Okay. So if you know that, now there are all other things are the cube. Okay, let me give you 5 minutes break.
Where is the lecture of? Where is the lecture here?
This one is not there. Should be in Canva. Can you upload it in Canva? So today's slowly limit for a channel. So slowly limit for a but so just consist of moving. Our money, so that account function is like this. So it just moves a little bit. So if it moves a little bit, infinity the particle time motion control. So it is move for this, right? Permanent slope rate is silent
And more 5 টা বেগে যাচ্ছে।
It's negotiable.
So 5 to begin মানে কি তোমার এখানে কিন্তু সয়েল এখন it looks like this. আগে যেটা হচ্ছে straight ছিল তোমার slope এর মধ্যে এই করে হবে। Now এই মুভমেন্টটা মানে basically this is your cutoff point মানে তার উপর পর্যন্ত পড়ে যাবে।
মুখটা করতে এটা কি জিও কোন
Okay, so in terms of the slope stability analysis, there are many different methods. You know, so the first method is the most basic, the only method that can be done by hand calculation is the method of slice or the ordinary method of slice. You know, so the ordinary method of slice is in the ordinary method of slice we try to consider 2 things. First, in the method slice, when we are trying to find out, like, let's say we talked about there is a slope failure. So if there is a slope failure, it is going to create a slip surface. So now we wanted to identify that the load distribution within the slip surface. And when we are trying to identify the load distribution of the slip surface, we also need to find out like some interaction, what is happening there, you know? So, how do we know if the slope is stable or not? It comes from, we need to find out what is the force that is acting on the slope to create it. And you also have to know what is the resistance from the soil is there to keep it in place, you know? So, technically we can define the factor of safety, and the formula for factor of safety is very simple. Factor of safety is equal to friend over enemy, right? This is the basic formula for factor of safety for anything. You know your friend, you know your enemy. Yeah, all you have to do is you have to find it out. And if your friend is greater than your enemy, then you have a higher factor of safety. And if your number of enemies is bigger than your friends, then you're in trouble, right? So what is the balance condition?
Both are equal.
Both are equal. So if your friend is equal to your enemy, then what is the factor of safety? 1, right? So you will marginally survive. In any case, any of your friends become angry, you're doomed. In any case, your friends are happier with you, you're successful, right? So most of the time we try to keep the balance and try to keep more friends. Right? So you don't know, we may make it create some enemies along the way. Since we are a human being. But what happens to the slope? The slope makes the enemy too.
The WN is the friend.
Forget the theory. Is there a condition that the slope may have some enemy?
Rainfall. Rainfall.
Rainfall, okay. Rainfall can be enemy. Earthquake can be enemy.
Poor
Yes.
water pressure.
Poor water pressure is the inert, is not the enemy. Enemy is like
Excavation.
excavation can be enemy too. Yes. Like anything outside that is coming and changing the condition. You know. So let's say you have a equal number of friends and equal number of enemy, and your friends are happier with you. You know, so you're in good shape. And then let's say you're in a condition that here's some extra pressure. You know, maybe you had a fight with someone, and he or she added some extra enemies in the market or in the area. So that may create some problem for you, right? Those are external events, you have no control. So for slopes, there are like some events which have no control, like maybe rainfall, earthquake, excavation, and is there any other thing?
Poor water pressure.
Erosion.
Erosion is not going to create risk of failure. Erosion is different.
Soil weight. Increase in soil weight.
Increase in soil weight.
This will come from rainwater.
Okay, what is the increase in soil weight? It's a good example. How we can have increase in soil weight.
Past water condition.
That is the output from the rain. Output of the rainfall.
Increase of overburden pressure.
Increase of the overburden pressure from
Superstructure.
from superstructure, like someone building something on top of it. Is there any other thing may happen that may increase the overrun?
Nothing, sir.
Okay, how many slopes do you dump soil?
Increasing deposition.
Deposition.
If more soil deposits over,
Okay. Yes, but how about you bring equipment on top of the soil, slope? Equipment. Let's say you bring a rig on top of the slope. What might happen?
You-
You just throw a excavator here. Is it good? It's risky. Fine.
Slip surface.
Yeah,
Oh. Additional weight.
additional weight.
When it is excavating, when it's excavating, the weight of the soil is decreasing, the more pressure it is, in that case.
Okay, that's a different thing, but the first thing is whenever you're bringing something on top of it, you're adding the weight. If you're adding the weight, that's the problem for you. You know? Okay, because it's going to push it. Whenever you are having the weight, slope has instability. This is trying to move, right? And when you add some extra weight on top of it, it will try to move more, right? So if you're adding something on top of the slope, is it your friend or enemy? Enemy. If you bring something here, the same excavator comes here, and the bottom of it. What happens now?
Friend,
Why?
it's not everything.
So if someone is not doing any harm to you, it's your friend. Yeah, maybe a passive friend. Not the active enemy. But why? It can be a friend, but I want to know why.
Giving the resistance. Giving the resistance,
How?
Sliding action.
buttress type of thing.
Buttress type of thing. What is the buttress type of?
That's giving, resistance to the corner. To the one corner.
It's not overtaking the hinge.
Thing?
Support with supporting here.
So it's like you have a sleep, you're trying to sleep down, right? And you have something, so when you're is doing a coupling action, like it's trying to decouple, you know. So when you have a slip surface, it's moving like this, right? It's going upward. If you're pushing it down, you're pushing it backward, right? So that the weight will help restrict it. So if we see the slope is failing, what is the best way? Immediate action you should do.
We choose,
You can dump
put
something
some load,
Come back.
put some load.
Bag of soil.
at the
Bottom corner.
launching
at the
apron,
toe,
launching apron type things. Apron type things, launching apron.
launching apron. You add some weight, whatever the thing you do. You add some weight, that helps, right?
there's some support at the toe.
Weight, not support. Support is a different ballgame. If you add some weight at the toe, it will try to keep it from failing, right? Have you heard the word barm? Barm, B-E-R-M. What is the purpose of the barm?
Is used in a like slope to increase the slope height. Like we segregate the slope to like 2 or 3 parts so that
No, that's not bar.
like one slope we go certain height and then
That's not bar.
the horizontal.
That's the staging.
Yeah.
Any idea of having bar or
It's like, at some, at a barrier in the slope.
okay? Do what?
To neutralize the slope failure.
Neutralize this one. Okay. Let me try to draw something. The way, let's say we have a retaining wall. And we just build a retaining wall like this. Here's our soil, the bottom part, and here's our soil at the top part. You know? For someone design it like this, condition A. And someone design it like this, condition B, having a retaining wall. And then putting the soil here. Which is the condition B? Which condition is going to give you better resistance for the retaining wall?
B,
Why?
because there is extra soil resisting the.
Two, right? So the extra soil is giving what?
Weight to the failure slope.
It's actually resisting the sliding effect.
Okay, very good. It's actually resisting the sliding, right? So when it's trying to move, it resists the sliding. Some designer also try to extend it like this. Extending it as like a key at the bottom. You know, if you have a key at the bottom, it does something. It tries to resist the sliding, but it does something. What it does?
Increases the speed of the area,
Nope,
like the radius.
nope. It does something. What is that? It does something like between A and B, B has some advantage, extreme advantage than A. What is that? And how is happening?
Less exposed area.
Less length from volume.
What?
Less length from volume.
Oh. Yeah, it's like always right, but it's not the
That's a
major
important.
contribution.
It helps prevent the overturning.
Okay, yeah, it's
Soil over the foundation. Small space.
it's all about the foundation. Yes, but it has a major advantage. All of this you're saying is the outcome of that. But my question is, how is getting that?
Increasing the depth for the passive resistance of the soil layer.
Oh, you're back.
Yeah, I was here all the time. I was just, I'm not feeling good. But I mean, when we have this key, we will have more depth that we count for the passive resistance. So it
Okay,
will
this is
increase
the one I was looking for, the passive resistance. Whenever you have the soil on this side, it gives you the passive resistance. So what is the passive resistance? What do we know about the passive resistance?
An infrastructure giving space on the soil. Means that
When you push the soil, soil push you back. And soil push you back hard. You know, so don't try to mess with the soil. So what they're trying to do is they're trying to mess with the soil. And the soil is pushing it back. You know, it's a basic phenomenon. When you are pushing the soil push you back, right? So what is happening on this retaining wall? This retaining wall is trying to push it, the soil, right? So whatever the soil you have on this side, we'll try to push it back. Like this, pushing it back. That's the reaction from the soil. The soil gives you a significant reaction like this. And that's one of the biggest advantage using the soil. You know, in the earth structure, you can use the passive resistance of the soil in your design because it always gives you the resistance, no matter what. You know, so that passive resistance comes from when you're pushing the soil. You know, earth pressure is a very interesting theory for soil. Soil has three conditions. One is the active condition. Soil is at place. It's not moving. You know, so that's like what we discussed. You have no imbalance, right? Both of them are in place. Versus you have an active condition. Means you take some load out from the soil. You know, so if the structure is moving away, then the soil is not going to push it harder. You know, so if you're, let's say if this is my hand is soil and this is the structure. I'm trying to push it, you know, my structure is very stiff. Let's say. Then the soil will push it hard, you know. Soil will try to push it more until it reaches the at rest condition, inert condition. But if I allow some movement, you know, the soil is there, I'm allowing some movement, the resistance of the soil will go down. That's called the active condition. And you're pushing back the soil. So soil don't like that. So soil will push you back if you're pushing back the soil. And soil will push you back really hard. So that is like, that factor is almost double. No, it's almost 5 to 6 times higher than the active pressure. You know, so the formula for K naught is 1 minus sine theta. 1 minus sine theta. You know, your active earth pressure is 10 square 45 minus P by 2. Okay, and Kp is equal to 10 square 45 plus P. So let's do a calculation. P equal to 30 degrees. Okay. So if you consider P equal to 30 degrees, what is this value? 0.5. Your K naught is 0.5 for P equal to 30. Okay. What is this number? 45 minus P by 2. So no, 45 minus P by 2. So it's 30 degrees. So tan 30 is 1. Okay, so this number is 0.3, right? And then you have 45 plus 3 by 2. So tan square. So this is 3, right? So what is the ratio? It goes from 0.5 to 3, right? 6 times higher. And is almost close to 9 times higher than active pressure. Right? So if you make a structure which is flexible, it attracts more load. If you make the structure stronger, it attracts more load. Right? So if the structure is flexible, it doesn't attract that much of load because your load goes down. You know? But if you're making the structure stronger, it attracts more loads because the soil will be will give you the active earth pressure, not the active earth pressure, at rest condition, right? And then if you're moving, if you're even pushing it harder, not only making it like just staying there, but you're also pushing the soil back, then the resistance from the soil will be much higher. You know? So on the retaining wall, this side is on the active side, A condition. The opposite side is the KP condition. So when you create a farm like this will create what? Passive condition. So your resistance will be much higher. You know, so whenever you have like a failure type of condition, if you add some weight at the bottom, that creates a bar, which is a passive condition. So the passive condition immediately cut off many failures. You know, but if someone doesn't know how it works and start adding the weight on top, then it's going to be really problematic. So for a slope repair project, which side the construction should begin?
Top.
From a slope repair project, from which side your constructions should begin?
From top.
From the toe.
Because that would be risky.
No, at the toe, your weight is helping the slope, so it will not cause a failure.
We start from the top, we must like it.
If you start from the top, you're adding the problem. If you're going from the bottom, you're trying to solve the problem.
No, I thought that if there is a berm at the bottom and we are going to excavate it.
Yeah, you see, if you have a berm at the bottom, then you doesn't have the problem. Okay, so let's go back to the discussion. Today I went through so many topics here and there instead of discussing the lecture note. Yeah, the lecture note is very good. It doesn't have much things to discuss. It's very simple. All it does have is like a theory. So the basic theory is you have a slip surface. So you wanted to find out like how you can calculate the factor safety of the slope. The first thing is you need to identify the friend, and then you have to identify your enemy, right? So who is your friend? Your shared strength. Very simple, you know that. And shared strength comes from your formula, tau equal to C plus sigma tan phi, right? So that is your friend. We know that. Now the problem is we need to calculate the enemy. How we know the enemy? So basically what happens is for the whole block, we need to find out the weight first. And the weight has two components. One component goes W, the other component is like, okay, so we have an angle, let's say the angle called theta, right? So in this case, this theta and theta is equal, right? So in this case, we got a W cos theta, and then we got a W sin theta. Okay? So W sin theta is your friend or enemy? W sin theta is your friend? How?
Towards the,
Towards the side? It's trying to pull to keep it, right? Pull it inside. So that's trying to pull it inside, that is your friend. W cos theta? Is your enemy? Okay, so if W cos theta is your enemy, then this double cos. Wait, your theta is not here. I don't draw it right. Double cos that is that. But let me try to draw it right. So this is it. You get a angle, and then you get your right angle, right? So in this case, which one is your theta? So let's say if this theta, the thing is this theta, right? It's 90 minus theta. So if this is 90 minus theta, this is theta, right? So basically, your theta goes other way. So here is your, this angle is theta. This is double cos theta. And this is double sin theta. Alright? So your double cos theta is your friend. And double sin theta is your enemy. Okay, so let's say you have the double sin theta. Now you wanted to find out like what is the total double sin theta. So you need to find out the area of it. You know, the whole area first. Then you multiply it with the gamma to get the weight, right? So you can calculate the double sin theta, isn't it? Now, how you can get the double sin theta? How you can get the double sin theta, but the double, how you can calculate the double? Gamma, double equal to gamma is?
No, gamma into
Area. So how you can calculate the area?
Slides.
Why?
The area is irregular.
Not uniform.
It's not uniform.
So it's not uniform. So how you can, how slicing we have?
Make it uniform so that you can.
Regular integration.
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 Find external element from the small elements and use of
But why we are slicing? Like,
Make it rectangular.
okay, very good, to make it rectangular. That's the. We need to break it down into rectangle and triangle or trapezoid. So we know how to calculate the area, known shapes. We need to break it down into known shapes and small enough so that if we even make it a smaller shape, there might be some errors, but that errors are not very significant. You know, 0.1%, 0.01% type of error. If we make it small enough, you know, very smaller, and then we calculate the area of each of the elements, smaller elements, right? That's how the method of slice started. That was the basics. You get a slip surface, you wanted to solve it by hand, you break it down into smaller pieces, you calculate the area of each of the pieces, you add it up so you can calculate your area. And then you also know what is your shear strength, so you know your strength. And you go from there.
Here string plus W cos theta would be
Shear strength plus W cos theta. What is W cos theta here? Wait. So your shear strength equals what?
R equal to C plus
Tan phi?
Sigma times.
sigma times.
Sigma times what is sigma?
Sigma is normal stress.
How much? How much?
Sigma is normal stress.
Is equal to
Okay, so the question sigma tan phi.
So there is an enemy influence.
There's an enemy in friends. So, that's a traitor. Worse than enemy.
Not it.
Not good. So, who is your enemy in friends?
That normal, that sigma.
No, that sigma is always your friend. But what is the definition of the sigma? It is like, let's say we have a weight, okay? Plot. So how we get it as the equal to diagonal is C plus sigma times K, that formula, right? It comes from something. Do you know where it is coming from? What? No.
Can you ask?
The tau, diagonal C plus sigma times K. This formula comes from where?
More circuit. No, Coulomb theory.
No,
Coil model.
I know.
Coulomb's soil model.
Coulomb solve more Coulomb,
More Coulomb.
failure envelope, right?
Yeah.
That comes in a different way. The more Coulomb failure envelope. You know, but how this is the shared strength of the side. How this formula, this theory is being established. What is the basis of it? This all comes from the friction, physics, basic physics. So what happens in the friction formula? What is the friction formula?
Someone try to move over there. It is proportional to the normal force.
Proportional to the normal force, right?
Angle, there is something called angle of repose.
Angle of repose. Angle of repose comes later. First, let's say you have a weight, right? And you have a force, F. You're pushing it. If you're pushing it, someone will come and resist it. So someone will come and resist it is a force, right? Which is known as the friction force. Let's say F. So your FF is what? A factor multiplied by the normal force. So your normal force is R, right? So it's a factor mu multiplied by R. And what is mu?
Distance.
Or any surface that's constant for the surface.
That's the constant for the surface. And how we calculate that the constant?
Yeah.
Class 5, class 6 get there, right? It's elementary school lecture. So how we calculate that? Mu. Mu. How we calculate the mu?
10 equal to 10 z degree.
Angle of repose, right? Basically, that is tan phi
10 pi.
or tan phi, right? So what do you get? F equal to mu, which is tan phi, right? Multiplied by R. Tan phi multiplied by R. When you only have the friction, with friction now we add the cohesion. What will happen? You add the cohesion with it, right? So add the cohesion. Let's call CA. But this is a force. If you want to convert it into a stress, divided by the area, right? The surface area, the contact area. You know, so you get this stress. So that contact area is nothing but shear resistance. That shear resistance is coming as a tau equal to CA, this is C, cohesion, as a stress, plus sigma. Sigma is what? R over A. R is a normal resistance. Remember that, normal resistance. Sigma tan P. That is your formula. Coming from what?
Physics.
Physics.
chapter 4 of our physics book.
So whatever the chapter 4 of that book,
Those were discussed.
those are discussed, right?
Physics first paper.
Physics first paper. Okay, good. So that helps, right? Okay, so you got the C plus sigma tan phi, right? So what is the sigma? The reason I explained it in this way, just to give you the feeling that how to calculate the normal resistance. So your normal resistance works in which direction? It's very important. The normal resistance works in which direction?
Particular to the surface,
Perpendicular to the surface,
the side,
right? Because if you're sleeping like this, your R is always perpendicular to that surface because it's coming from the friction field. Got it? So your R, so right here, on this case, on this slip surface, how you calculate the sigma? Because we need to calculate the sigma tan phi, right? So how we calculate the sigma? At whatever the point we are looking at, we need to find out the perpendicular to the slip surface. To that point, we need to find out the perpendicular. We need to draw a perpendicular line. Tangent, we need to draw a tangent and then we need to draw a normal line to the right, right? That's how we get it. All right? That's the angle where it is working. But we also need to know how much force is working. So how do you know how much force is working? So let's say we take it down into smaller pieces, each slice. Each of the slice has its own weight, right? And so forget everything here. Let's just now focus only on one slice. So let's say we have a slice like this. This is our slice. This slice has the weight, right? This slice has the weight, but that weight will has a component. This is the W. W will have a component like this and like this. Right? But what is this angle? This angle is different. This angle is not connected with the theta. That's a different angle, right? So for each of the slice, this angle is changing. This angle is known as alpha. You know. So for each angle, we have a W cos alpha and W sin alpha. You know. So for each individual slice, we need to calculate the weight. We calculate the W cos alpha, and then we calculate the W sin. And for each of the slides, the W sin alpha is our enemy, and W cos alpha is always our normal resistance, right? And that normal resistance is contributing to what?
Safety. Stability.
Stability, right? Because it's a component, it's a function of the strength, sigma tan phi. That's the sigma. W cos alpha is the part of the sigma, which is your friend, no matter what. Okay. Now, the other question is, how about the solid weight?
How about the solid weight? That means there is water level involved.
Okay. If the water level is involved,
Weight is changed.
weight is changed. So what will happen? Adding the weight, W goes up, right? But there is another component. This sigma is the sigma prime.
Effective.
So when there is a water, you have a W cos alpha, But you also have a buoyancy effect from the water. So your W cos alpha goes down. Right? Because that W cos alpha is affected by the buoyancy, right? And then W sin alpha
It will increase.
will increase because your weight is increased. It's not a buoyancy. So whenever there is a water, that's a deadly combination for the slope. So whenever you have a problem with the slope, in most of the cases, that's with the water. Because water can create problem in both ways. It reduces your strength and it increases your energy.
Switching sides.
Switching sides, you know, as long as you add some bad influence, which is going to cut down your number of friends and convert them into your enemy. Avoid that. Okay, let's end the class here. Everyone is tired. We'll discuss again. But in the next class, I'll try to cover the slide. So we need to install that, and I'll share the, or Fine will share the installation instruction. So you can try to bring your computer. Okay, because I don't think we can install it in the lab computer within a week. Okay. But we need to submit it so we can get it done if possible. All right, thank you. Thank you all.
Thank you so much, Dr. Khan.